Welcome back. Today is the last day of September, and we're going to continue here in chapter 6. Last time when we met, we did the mechanism for the oxymercuration demercuration reaction. So we're going to continue working on these mechanisms, and after that, we'll go to the reactions. All right. So, number 6. Oh, before we go to number 6, I just wanted to highlight something that we mentioned here about the hydride. Notice that the hydride has 2 electrons and a charge. So a hydride is actually a nucleophile, and also it's a base. I just forgot to mention that last time. So just keep that in mind. And so let's go to our worksheet. Okay, so it says here, number 6, write the mechanism for the following reaction scheme and name the reaction. All right, I think I'm gonna take this so far away. Okay, anybody knows the name of this named reaction?
Halohydrin.
Halohydrin, very good. Who was that?
Paige.
Paige. How are you, Paige? Thank you
Thank
for
you.
participating. All right, exactly right. So halohydrin. So let's identify this reaction. Halohydrin. For some reason, I cannot see the name of the person that speaks now. It's weird. So the halohydrin comes from having a halogen, that's the halo part, and hydrin is the equivalent to the hydroxide. So I guess the that's part of the hydroxide, and then in it's just ending there. But that's the halohydrin. This reaction requires a halogen element like liquid bromide. I'm sorry, liquid bromine in water. So water is your nucleophile, and this also could be an alcohol. So if you've seen an OH somewhere in there and a halogen source, that is the halohydrin. And so this would be the reagents, and the reactants, the products will always have a halogen and an OH group attached next to each other. All right. Also notice that the OH will always go to the most substituted carbon, and the halogen will go to the least substituted carbon, because it goes via the bromonium ion in this case. All right. So let's work on the mechanism for this. All right. So one thing you have to worry about when you do a mechanism is to get to the final product. You have 2 options here for the intermediate. You have to figure out which one of the 2 you need. All right, so the one way to finding it out is by pushing electrons. So we're going to start pushing electrons. So this is my starting material. Here's my bromine. Even though it looks like this molecule of bromine has a net dipole of 0, because it looks like it will cancel out. This bond in between here is constantly stretching in and out, and so at some point in the reaction, one of them will be more partially plus than the other one because of that vibration. So it's almost like in a couple, there's always one person that is more electropositive than the other one. That's the way I think about it. And one is more electronegative. All right, so this double bond is your electron-rich source. And now here you have your E+. This is your E+. So for these alkene reactions, it's very, very important that you figure out which one is your E+ and how do you make it. That is very, very crucial. So, and every case is different, so you have to learn all the cases. This is also, by the way, one of the few instances when you attack electrons to electrons. Also, kind of weird in a way, because notice that this bromine is surrounded by 6 electrons, and the pi electrons are going to go after it. Very few cases in chemistry that happens, and so this is one of them. So when it does that, these 2 electrons that are here are going to be transferred to that bromine, and now you have made something super duper cool. I think. Hold on. So it'll be. So notice I'm gonna put intentionally. I'm gonna put this methyl group down, and my bromonium ion will be up. But notice that the bond on the top, this one, is more elongated. So, and also it's slanted. It's very important. This is not a perfect triangle. This is more like that. All right, you get that? Where your bromine will be here. So in terms of bond breaking, bond making, this bond wants to break. It's breaking. All right. So I'm gonna delete this because I need space. And so you have that first intermediate reaction. So as you are more advanced, you will simply say, okay, I make that plus my enantiomer. But to begin, I'm gonna draw the enantiomer also. So the enantiomer of this. And if you were having to write this on a milestone, I would recommend you to draw both. Here, this methyl will be up. This bond is on the plane. And then you have this elongated bond. Oh, that didn't look good. And this one is a little shorter. And here's your bromine plus. All right. This is your enantiomer. So which one should I pick? Well, you pick the one that gives you product. That is your goal as a student, to find out how do you get from point A to point B. Now, if you look at this reaction, I know that this intermediate, this bromonium, this is the bromonium ion intermediate. It's the one on top is the one that's going to give me the product, because my nucleophile is going to be pushing this methyl up after the attack. Now, my nucleophile is water. So I have a question. Notice that here on this reaction, you made this, the bromonium intermediate plus bromine, as a byproduct. Question I have, why is water the nucleophile and not bromine ion? Anybody?
Is it because there's more of it in solution?
Exactly right. There's more of it in solution, so the water is swamping the reaction. And so you actually diluting bromine liquid. This liquid is orange in color, and it has orange fumes. It's very toxic. If you ever use bromine in the lab, it has to be always used inside of the hood, not on the bench. So just a little bit of bromine is diluted into water, and so there's more water. So this water then is going to be able to attack, and when that attacks, it will push the methyl group up. It's gonna push the methyl group up, and I'm gonna delete this processing here, and this bond is gonna break and transfer both of these electrons that are holding it to the bromine. All right, and so you're going to be making this. So here you have the ethyl group that is in the plane of symmetry. The methyl group gets pushed. Now the oxygen here has two hydrogens. This is a molecule of water that has made the attack, and it has a plus charge on the oxygen. And so you have one carbon here, right here, and that's this guy, and then it opens to make just simple bond to bromine. One single bond there. All right, so you're almost done here. Notice that you need to freebase this molecule to get the product that is resembling quite a lot to the product. The only thing we need to worry about is to get rid of one of the H's. Again, water is both a nucleophile and a base. It's amphoteric. It could also act as an acid sometimes too. But in this case, this oxygen goes after this H. Actually, let me grab one of the two. I'm going to grab the one on the top because it's easier to see it. So when it does this, these two electrons transfer to the oxygen. The two electrons on the bond transfer to the oxygen. And now you have final product. So you will be making this where the OH is free now. It has two lone pairs. And you have that. You have made the bromine is underneath plus H3O plus. All right, very good. You've done this plus the enantiomer. So the enantiomer of this will be, let me write it down underneath. I'm gonna write the enantiomer in green, so because we didn't use it, so it'll look like this, where the methyl is up and the OH, I'm sorry, when the methyl is down and the OH is up. All right, this is the enantiomer. We don't care about it because that was not part of the question. The reaction might be 50-50. So we take the 50 that we want, the 50% that we want. All right. Any questions up to this point for the halohydrin? All right. Question I have here is, if you had, say you had methanol as your solvent, that is also your nucleophile, you would end up with a molecule that looks like this. And this is also a halohydrin. Do you see that? So that comes after deprotonating the H from the OH from the alcohol, and you just get the ether, the methoxy group here. All right. That is if you have made that, if you have used that alcohol. All right. All right. So you can take notes because I'm going to delete this, and this is being recorded, so no problem. All right. I have one more mechanism here. So take home lessons from these two mechanisms here. In the oxymercuration, demercuration, notice that we end up with, or in this case, a tertiary alcohol. This is a lock configuration. The reaction intermediate has a locked configuration. All right, it's locked right here. Notice that the water or the alcohol will attack in an SN2 borderline fashion. This results in no carbocations rearrangement. Whether this one also is a locked configuration. So no carbocations rearrangements. All right. So let's go to the next one. What is the name of this main reaction by any chance? Anybody knows it? What will be the name for this? Has a simple name. Hydration. Very good. How do I know there is hydration? Well, it says dilute sulfuric acid. If it's dilute, that means I have sulfuric acid in water. The universal solvent that makes something be dilute is water. All right. Okay. So before I do this mechanism, I see where I am. I have here's point A, and I want to go to point B. So based on this, I know. Notice what's happening. One H is going here to do the Markovnikov addition on the double bond. And the OH is going to go here. This is your molecular water hydrating this thing. The proton that you see here doesn't come from the water. It comes from the acid, actually, the catalyst. And on my recordings, I mentioned that, no way. Hold on. Can you guys hear me? I accidentally turned off my computer. Hello?
Yes, we can hear you.
Okay, thank you. So what I was saying, okay, so this reaction can be just catalyzed by one drop of acid. One drop. And so in GChem, you learn that H plus is your acid source. Well, in OCHEM, H plus is the same as H3O plus. Are you with me? Which is the same thing as H plus in water. All right? Which is the same thing as any acid in water. Because notice that if you have HCl in water, your H plus is your proton source, the Cl is your counter ion, which is a bystander ion. It doesn't do anything on the reaction. And so it's in solution. So H plus in this case will be the same. Also, H plus could be sulfuric acid in water, and etc., etc., all the other acids. All right. So let's go to the mechanism now. Notice that. So starting this mechanism, if I give you sulfuric acid in water or dilute sulfuric acid, this is equivalent to H3O plus. And that's the part in OCHEM where you have to know by memory some things and also use your intuition. So this is GChem. In GChem you learn H plus. Now for OCHEM, they're used to using H3O plus. This is your hydronium ion. All right, so that's the beginning of this synthesis and this mechanism. So we're gonna go ahead and push electrons now. The double bond is your E minus source. This hydrogen here is your E plus source. So double bond attacks the hydrogen, grabs it. These two electrons are now transferred to the oxygen. And I'm gonna rotate this ring now a little bit. And so I'm gonna draw the carbon too. So I have 1, 2, 3 hydrogens because now I started with 2. The one extra hydrogen comes from the acid. Doesn't come from the water. Comes from the acid. And so that puts a plus on the most substituted carbon. So this is your Markovnikov. And this reaction is ruled by Markovnikov. And then the plus is going to accept the nucleophile. The OH will go to the most substituted carbon. All right. So here's your, so from this reaction, once you deprotonated the acid, you also form water. You notice that? So water is a product of this first step. Happens to be a nucleophile too. It sees the opportunity. And you have plenty of water here because this is diluted. This water molecule comes and attacks that carbocation. And now you made this guy. So here you have an oxygen with 2 hydrogens, a plus, and lone pair. All right. And so we need to free base or deprotonate this intermediate. So we do it with more water. So water comes again. and it's gonna grab this H. And these 2 electrons that are on this bond are gonna be transferred to the oxygen. And check out what you made. You have made a tertiary alcohol with a methyl group. Plus, you regenerated your hydronium ion and now this reaction can go on and do a cycle. So this acid, this hydronium ion, can go back to the beginning and take another alkene and convert it back into an alcohol. So eventually you start with 100% of this to 0% of this and 100% of this being made just by using 1 drop of the acid. You get this reaction going. So this is an example of a catalysis where lysis means breakage, and kata, I believe, is like fast breakage, all right, or fast transformation. And so that's why this reaction is acid catalyzed. All right, any questions after this point? Notice that here you actually end up with an already stable tertiary carbocation. There's no problems. But what if I give you this? What if I tell you this? So let's say we have this instead, and I tell you to add H3O plus. What would you get? Question I have: what would you expect to be the final product? Let me draw them for you. Yes.
Professor?
Yes.
I was going to say you're going to make a tertiary alcohol, but you drew it.
Yes, exactly right. I was going to give you the 2 options. Yeah. Yeah, exactly. So you will be making this. And so that goes after what? Is that you, Benjamin?
Yes, sir.
I think I recognize your voice. Because I cannot see your name here popping on the screen anymore for some reason. So, yeah. So this reaction takes place after how many hydride shifts?
That would be 1.
1. Yeah, very good. So let's do the mechanism real quick. So the double bond attacks 1H. Whenever you have it like this, just simply put the arrow in between the H and the oxygen towards the oxygen. You see that? To simplify things, you go like that. That's telling me you're breaking 1H O bond and then giving the electrons to the oxygen. All right, but I'm not gonna be that lazy. Let me redraw it. I like to do the little extra mile, but because, all right, let's do the extra mile since I need to train you well. I'm gonna put the plus on this side. Lone pair. So this one grabs the H. These 2 electrons are transferred to the oxygen. That's what I meant by this. All right. And then now you put a hydrogen here. Now it becomes a CH3, and you have a plus here. Now you have an H here. Also, in the book, in the homework, we have examples of 1,2 alkyl shift. So this shift that we're looking at is a 1,2 hydride shift. But you could also do, say you have this. You have a CH3 and a plus here. This CH3 will most likely be willing to jump also. And now this becomes 1,2 alkyl shift or methyl shift. People just call it alkyl shift, where you have rearranged this molecule in such a way that now your methyl ends up here and your plus is here. You went from a secondary carbocation to a tertiary carbocation. Here is secondary. But when it does the shift, you have the H jumps here and the plus goes there. So all that now you have a CH3, CH2, tertiary carbocation. All right. So now when your water comes and attacks, you've made the tertiary alcohol. Well, this one still has an H, an extra H that you have to take care. And some more water comes into play here. And that's going to grab the H. Grab that H and switches those 2 electrons down to the oxygen. And you form this final product, a tertiary alcohol plus H3O plus. Hydronium ion. All right, very cool. All right, I have a small quiz here. This is a in-class quiz. So, question is, examples, further examples. Let me put that in there. What if I start with this? And I said I'm gonna use sulfuric acid in water. Look at the different kind of variations for the acid. Question I have: would you make, let's say, A? Don't answer yet. Would you make this? Would you make B? Would you make C? Or would you make D? Please get good at this stuff. Someone is answering with the chat. Yes, Megan, good job.
Thank you.
You're welcome. Megan said C. That is the answer. All right, that's the right answer. The question is, how many hydride shifts did that undergo?
Would it be 2?
Yes. It'll be 2. This one is 2 hydride shift. This one, A. Does A has any hydride shift? No. No hydride shift. B, how many hydride shifts does that have? 1. Very good. You see it, right? 1 hydride shift. And D, what kind of product is D? Anybody? Think Markovnikov. Someone in the early class figure it out. What is it? Is it Markovnikov or anti-Markovnikov?
Anti.
Very good. Is that you, Jeff?
Sir. Yes, sir.
My man, Jeff. Awesome. Is anti. Very good. Now, how do we get the anti-Markovnikov? Anybody? Let's make this reaction happen. This happened by two-step synthesis. Anybody can give me, from the same starting material. So it's 3 carbons and a double bond at the end. Who could tell me the name of that reaction and the reagents to make it happen? Any brave soul out there?
Would that be hydroboration?
Excellent, Jeff. Hydroboration. And so, can you give me the reagents?
Yes, I have BH3 or B2H6, and then you're going to have your H2O2 or your strong base in NaOH.
Yes, and usually this goes in THF, which is the solvent. And
right.
Yeah, and you have hydrogen peroxide and sodium hydroxide. All right, hydrogen peroxide, H2O2. All right, let's take a little break here. Just remember something. They say 2 guys walk into a bar, and the bartender asks one of the guys, "What are you having, sir?" He says, "I'll have a glass of H2O. And you, sir?" "I'll have H2O2. And then he died. All right. So he drank hydrogen peroxide. You guys are muted. All right. So hopefully you are enjoying the joke. Megan laughed. Thank you, Megan. Oh, awesome. All right. So this is the hydroboration. Check out what's happening here. For the hydroboration, you have this. This is why it's anti-Markovnikov. Say you start with this. Between the hydrogen and the boron is more plus. It's more electrophilic, and so that's going to play the role of the E plus. That's going to be your electrophile. The hydride is negative. It's a nucleophile. It's a base. That's why I started the class like this earlier. This is a hydride. And so the hydride is going to go to the most substituted carbon. That's why this is an inverse Markovnikov addition, because the product is the inverse of a Markovnikov, where the OH goes to the least substituted. This is the least substituted carbon. All right. So after this happens 3 times, because you have a source of 3 hydrides there. So the first one looks like this. Check this out. I don't expect you to know the mechanism for the hydroboration, but this is how it works. Count your carbons. You have 1, 2, 3 carbons. So put 1, 2, 3, and then you put a boron with 2 hydrogens there. That's the first step. First step does that. Second step, it goes and cyclizes. Not cyclizes. It goes and rotates and does another hydride attack or another hydroboration attack. So you have 1, 2, 3, and the ring. That ring is ugly. And then it does one more attack because you have an BH. As long as you have a hydride source, you can do this. 1, 2, 3, and then the ring. All right, you see that? Now, so this is step 1 on the hydroboration. Step 2, what it does is the hydrogen peroxide and the sodium hydroxide, they destroy this complex and they break it up. They break it up here, they break it up here, and they break it up here. You end up with 3 molecules of 1, 2, 3, 4 bonds of the alcohol, and some of the byproducts for this will be something like sodium, if my memory doesn't fail me, boron, like trioxide, something like that. After it gets broken up into pieces. But this is inorganic chemistry, so we're not interested in that. We are interested in the organic part, the only chemistry that matters. Haha, good commercial for organic chemistry. But it's true. Let's see, 5 years ago, there were 10,500,000 molecules synthesized in the world. So 10 million were organic molecules, 500,000 were inorganic molecules. So yes, there's more organic chemistry going on. It's the science that sustains life pretty much, and so it's more abundant. All right, so let's notice that this guy is this, and it comes from hydroboration. All right, any questions up to this point? So what happens here? Oh, a question, yes. Question?
Yeah.
Yes.
So I was gonna ask, is the 1,2 independent of naming for like the 1,2 hydride or 1,2 alcohol shift?
This one and this one? What is your question again?
Oh, so like where you have it drawn in blue, where you were showing us the hydride shifts, and you have it named like 1,2 alcohol or 1,2 hydride shift.
Yes.
Is that independent of naming?
Yeah, that's independent of naming. Let me show you where that comes from. The 1,2 punch comes from here. So here's carbon 1 where the jump starts, and carbon 2 where the landing is. You see that? That is 1,2 hydride shift. Now, if you have something like this, we'll see this later on. Let's say you have some molecules could rearrange, like let's say you have 1, 2, 1, 2, 3. So let's say you have something like this H jumping over here. This would be a 1,3 hydride shift because you have 1, 2, 3. It depends on the reaction. There's 1,3 hydride shifts, there's 1,5s, even 1,9 sometimes, depending on the reaction. And I will when we do the second semester, let's say I have, actually, to make this one, let's say we have this. Let's make it so that it can that it can make a stable carbocation. So here we'll go to this one. And now that secondary, so you go from a secondary to a tertiary carbocation like this. Do you see that? This is a 1,3 hydride shift. 1,3 hydride shift. You see it? Here's the jump. Starts on carbon 1 there, and it lands on carbon 3. So it's a 1, 2, 3, 1 to 3 hydride shift. Does that make sense?
Yes, sir. So it's just telling how many carbons it's jumping.
Exactly. It's not nomenclature. Yeah, it's not nomenclature. Yeah.
Okay, thank you.
You're welcome. All right. We got a couple more minutes. So let's go back now. We're doing really well based on time here. Let's do now number 2. Predict the reagents of the following reactions. Whenever possible, allow C+ rearrangements. State if the reaction proceeds via Markovnikov, anti-Markovnikov, or neither. All right. So last time when we talked about this, we say, okay, the column on the left is reactants. The column on top of the arrowhead is the reagents. And the column on the right will be products. All right? Okay. So, can you name a named reaction where you could have, well, you can put a carbon, hydroxy group, an alcohol, next to a tertiary carbon without a carbon-cation rearrangement? What would that kind of reaction be? You notice that? Notice that I purposely put all these 3 reactants the same. And we're going to get different products based on what I just taught. So you could tell me, okay, you can start from number 3. This is the cool thing about, and this is what I always teach and preach. If you're doing taking an exam, you don't need to start from number 1 if you don't know number 1. Let's do number 3 here. Notice that number 3, do you see a rearrangement on number 3? Because obviously, yes, right? If you add the hydrogen here, you're going to go to carbocation here, to 1 here. All right? To put this OH here on the tertiary position. So yes, there is carbocation rearrangement here. What would be the name for this reaction? What if I help you and say?
Maybe hydration.
Hydration. Very good. Yes, sir. Hydration. All right, give me the reagents for hydration. Acid and water, right? So you can
dilute sulfuric acid.
Yep, you can say that. You can say dilute H2SO4, and that's good. Or you can say H+ and water, or you can say H3O+, and that's it. One of those 3. It's your choice. All right, so that's good. Does this reaction proceed via Markovnikov or anti-Markovnikov, or neither? Yes, it's Markovnikov. Because protons do matter here. You have 2 versus 1. All right. Okay, so we got 1. How about 2 or 1? We just did 2. You notice that? What would be 2? Jeff knows this one. Hydroboration. Hydroboration will always put the OH at the end on the least substituted carbon. All right. Is this anti-Markovnikov or not? We know that this is anti-Markovnikov. Anti-Markovnikov. What would be the reagents for this? Well, Jeff gave them to me earlier. BH3 in THF. Hydrogen peroxide, do not drink that. And sodium hydroxide. Are there rearrangements on this here? No. No carbocation rearrangements. I'm just going to put like that, rearrange. That means rearrangement. I have 1 more minute. Please just give me 1 more minute. Let's finish this one up. Does this look like Markovnikov to you? I'm putting a hydrogen here and an OH here. So yes, the hydrogen is going to the least substituted carbon, and the OH is going to the more substituted carbon. Markovnikov. This is a cool name for a dog. Come here, Markovnikov. All right. So, can you give me now reagents for this reaction? Really quick. Anybody? Where is my man Wise? He knows this one. He knows
It's mercuration, demercuration.
Yes, sir. You got it. This is mercuration / demercuration. All right. So the reagent will be HgO acetate twice in the presence of water, and then sodium borohydride will do the demercuration. We're going to stop there. I'm going to stop right here. I'm going to answer any questions you might have.